Hello and welcome to York Observatory's monthly Teletube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. York YouTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle at York Observatory and Facebook at Alan I. Carswell Ops. We would like to inform you about the opening and call for applications for the Summer 2023 Astronomer in Residence program. This program is a collaboration of the Alan I. Carswell Observatory with Killarney Provincial Park to host astronomers in the certified dark sky side of Killarney to lead in-person presentations and shows using the park's observatory. To learn more about the program, its requirements, and the application process, visit our website at yorku.ca/science/observatory/air. Good evening, everyone. I'm Maheen, and I'll be one of your hosts this evening, along with Jatin, Paul, Zena, and Zainab. We are here from the Alni Carswell Observatory at York University. Tonight, we've got a great presentation about Asteroid Bennu. However, before we move on to our What's Up and section, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many indigenous nations. The area known as Takaranto has been taken care by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. Now, without any further ado, welcome again, and I want to give you a little update on what you can see this coming week. Starting off, the moon tonight is a full moon and actually a supermoon, which is due to its location opposite to Earth as the sun, resulting in it being fully illuminated with an illumination of 99.51%, making it an excellent target to catch with your naked eyes. The moon tonight will be near its closest approach to Earth, making it look slightly brighter and larger than usual. Unfortunately, the moon sometimes can look a little flat when seen through binoculars during its full moon phase due to its high brightness. Therefore, it's always a good idea to observe it closer to moonrise time for the best view. This will also be the last of the 4 supermoons of 2023, so definitely check that out. Some fun stars you can catch in the sky this week are Arcturus and Vega. To locate Arcturus, search for the constellation Big Dipper in the night sky. The handle of the Big Dipper, which appears like a curve when extended past the end of its handle, will lead you to Arcturus. Vega is the brightest star in the constellation of Lyra and can be spotted by spotting the summer triangle in the sky, which is a prominent asterism consisting of stars Vega, Altair, and Deneb. A space event to look out for next week is the Draconids meteor shower, which peaks on Friday, October 8th. It is a minor meteor shower which produces about 10 meteors per hour and is produced by dust grains left behind by the comet 21P Giacobini-Zinner. The best time to view this meteor shower will be at nightfall and early evening Friday from a dark location away from city lights. A good place to land constellation Big is when the moon is too far away from the Earth to completely cover the sun, resulting in a ring of light around the darkened moon. In Toronto, however, this will appear as a partial solar eclipse. Make sure to take any necessary precautions for the safety of your eyes if you do decide to observe this solar eclipse. I will now night.
Hi everyone, my name is Jatin, and today I'm going to be talking about the history and formation of Bennu, along with a little insight into its composition and why asteroids such as it may be extremely important for life on our wonderful blue planet. So let's get started, shall we? First, let's talk about why we gave Bennu its name. In 2004, there was a competition held by NASA to name the asteroid, and the winner of the competition was a third grade student by the name of Michael Curzio. You see, the spacecraft Osiris-REX has an instrument called the TAGSAM arm, and to Michael, he thought it looked an awful lot like the Egyptian deity. He had thought the dots were he had connected the dots, and well, here we are. On the left, you can see a depiction of Bennu from 1878. On the right shows a picture of Michael, and the person right next to him is Bill Nye himself. You may wonder what Bennu was called before the competition. And well, it was unintuitively named 1999 RQ36. Well, it's complicated, I know. Your next question may be when and how we found Bennu. On the 11th of September 1999, we discovered our beloved asteroid's existence with the help of the Lincoln Near-Earth Asteroid Project, also known as LINEA. The LINEA project was a collaboration between NASA, the United States Air Force, and MIT's Lincoln Laboratory. The collaboration had run through from 1988 till 2005, but when the Catalina Sky Survey project was up and running, the LINEA project had slowly started to be phased out. In fact, it was going up until 2018 and had found 2,423 other near-Earth asteroids, much like Bennu, by 2011. The right picture is GEODES, which is a telescope system that was owned and operated by the United States Air Force. And on the left is GEODES in action with a random asteroid. All that being said, how old do you think Bennu is? Here's a hint. This celestial wanderer is considered as an ancient relic, floating around since dawn of the primordial state of the solar system. Have you figured it out yet? Well, Bennu is around 4.5 billion years old, forming an estimated 10 million years after the formation of the solar system, which at the timescales of the universe is near instantaneous. It did come into existence out of nowhere, however. It is theorized that Bennu had broken off a much larger parent asteroid in the asteroid belt between Mars and Jupiter around 700 million years ago to 2 billion years ago, which is a huge difference. Shortly after breaking away from its parent asteroid, it had quickly started developing its own orbit, which just so happens to be very similar to Earth's in terms of time for a full revolution around the Sun. But Zena will be expanding on that topic a lot more than me. An asteroid doesn't break away out of nowhere, however. Something must have happened for Bennu to break away, and something did happen. Our leading theory is that Bennu's parent asteroid collided with another asteroid in the asteroid belt, leaving a large debris field flying off and accumulating into one. There's proof supporting this idea, as you can see in the picture on the left. You can see bright white sediments of rock on the surface that look mismatched compared to the rest of the surface of Bennu. According to Daniela de Agostena, a planetary scientist from the University of Arizona, these rocks originated from a fragment of Vesta that collided with Bennu's parent body and were also inherited when Bennu formed. Amy Simons, a researcher at NASA's Goddard Flight Center at Maryland, said in an interview, Bennu carries a wide mix of signals that could be the result of compositional variation, weather differences, age differences, a variety of particle sizes, or some combination of all of them. This is backed up by the pictures of its surface, which we analyzed by mapping the wavelengths of light bouncing off its surface and found that there is a lot of carbon-rich materials, such as carbonates and organic materials. We have detected the presence of hydrated phyllosilicates, which is a type of clay on Bennu's surface. We have also found that the core of the asteroid is made up of a variety of different materials, as its gravitational pull is not uniform across its surface. The way we figured this out is quite interesting. Lead researcher Daniel Schrees of the University of Colorado Boulder and his team used the dust which flies off the surface of the surface to model the tug of gravity that they had also found gravity. And what they also found was the region at the equator and the center was less dense than the poles. Research such as this helps us understand Type C asteroids better, but most importantly, helps us understand the role of meteorites in the fruition of life on our planet. And to those wondering, Type C asteroids. One second. Technical difficulty, sorry. For those wondering, Type C asteroids are the most common variety, and their composition includes a large amount of carbon. And with that, over to Zena.
Thank you. My name is Zena, and I will be telling you a little bit more about Bennu's features. First off, we're starting with the structure. Asteroid Bennu's structure is fascinating and distinct from what we might imagine when thinking of a typical solid rock. It is classified as a rubble pile asteroid, which means it's not a monolithic, cohesive body like a planet or a solid rock. Instead, it's a complex amalgamation of various sized rocks, boulders, and smaller rocky fragments. These components are loosely held together primarily by the asteroid's weak gravitational force. The term rubble pile accurately describes this kind of asteroid because it's akin to a celestial rubble heap that has accumulated over billions of years. These loosely bound rocks and boulders might have come together due to the mutual gravitational attraction between them, slowly forming the shape we see today. This porous structure also has implications for the way Bennu absorbs and reflects sunlight, which can influence its temperature and other physical properties. And when it comes to the size, Asteroid Bennu is relatively small when compared to some of the other celestial bodies in our solar system. It has an average diameter of approximately 492 meters, about 1,614 feet. To put this into perspective, Bennu is roughly the size of a small mountain or a skyscraper turned on its side. What makes Bennu particularly interesting is its irregular shape. Instead of being a perfectly round or spherical object, Bennu has a lumpy and somewhat asymmetrical appearance. This irregularity is a common feature among many asteroids, as they lack the gravitational forces necessary to pull them into a spherical shape, unlike larger celestial bodies like planets. And when it comes to the distance to Earth or the Sun, Asteroid Bennu follows an elliptical orbit around the Sun, which means its distance from Earth is not constant but varies over time. On average, Bennu is located at a distance of about 207 million kilometers, approximately 128.6 million miles from Earth. This places it well beyond the orbits of most planets in our solar system. However, what makes Bennu particularly interesting and notable for scientists and astronomers is its close approaches to Earth. Due to the elliptical nature of its orbit, there are times when Bennu's path brings it relatively close to our planet. During these close approaches, Bennu can come as near as about 150,000 kilometers, approximately 93,205 miles to Earth. And if we want to expand a little bit more on the orbit, we can say that what makes Bennu's orbit particularly noteworthy is its inclination relative to Earth's orbit. The orbital plane of Bennu is slightly tilted concerning Earth's orbital plane, causing periodic intersections or close approaches between Bennu and our planet. This orbital characteristic is why Bennu is categorized as a near-Earth object, or NEO for short. NEOs are celestial objects whose orbits bring them into proximity with Earth's orbit, increasing the potential for close encounters with our planet. The orbital dynamics of NEOs like Bennu make them of great interest to space agencies and astronomers. Understanding their orbits and predicting their future positions is essential for several reasons, such as impact, hazard assessment, and of course, scientific studies. And finally, I will be talking about surface structures. Asteroid Bennu's surface is a fascinating and dynamic landscape, offering valuable insights into the history and nature of these small celestial bodies. Some of its surface features include a rugged terrain. For example, Bennu's surface is notably rugged, characterized by uneven topography and a variety of geological formations. It is far from being a smooth, featureless rock. Instead, it appears as a complex landscape with slopes, ridges, and valleys. Second, the regolith cover. The asteroid's surface is covered in a layer of fine-grained material known as regolith. This regolith consists of a mixture of small rocks, pebbles, dust, and other particles. It is the result of countless micrometeorite impacts and the gradual breakdown of larger rocks over billions of years. Regolith is of significant interest to scientists because it can preserve the history of Bennu's interactions with other objects in space. And third of all is boulders. So one of the most striking features of Bennu's surface is the presence of large boulders scattered across its terrain. Some of these boulders are several meters in size, making them challenging obstacles for any spacecraft attempting to study or sample the asteroid. These boulders are thought to be remnants of larger parent bodies that were fragmented through collisions. And a last word on that is that understanding Bennu's surface features and composition is not only scientifically fascinating, but also essential for assessing potential future asteroid impact hazards and for planning future asteroid exploration missions. Now I will hand it over to my colleague Paul, who's going to talk about the mission and explorations of Bennu.
Hi, everyone. My name is Paul Mackin, and I'd like to tell you about the Osiris-REX spacecraft, its instruments, how it got to Bennu, and some of the exciting things it did when it got there. Osiris-REX is an acronym for Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. Although it's a bit of a mouthful, it does accurately describe a number of key features of the mission and its spacecraft. The spacecraft itself was manufactured by the Lockheed Martin Corporation and is operated by NASA's Goddard Space Flight Center. Science operations and data collection are managed by the University of Arizona's Lunar and Planetary Laboratory. The spacecraft itself is larger than a bread box. It's about 2.5 by 2.5 by 3 meters in size. Call it 8 feet by 8 feet by 10 feet in size. And it weighed 2,110 kilograms at launch. Actually, the spacecraft only weighs 880 kilograms, but there's a lot of fuel on board, and fuel is most of that launch weight. NASA designs missions with extra fuel and is very good at managing resource consumption, often, and in this case specifically, allowing for follow-on or extended mission profiles. Since Bennu is in close orbit to that of the Earth, sunlight is readily available. So the solar panels are really quite modest at 8.5 square meters in size, and they provide about 1,225 to 3,000 watts, depending on the distance from the orbiter from the sun. That's not really a lot of power, but the instruments are designed to operate efficiently, and it's sufficient for all the aspects of the Osiris-REX mission. The instrument suite is designed to support mission objectives. OCAMS is a set of cameras, including a medium-range mapping camera called MapCam. Polycam is a long-range telescope used for hazards near Bennu, and also for detailed imaging when in orbit. SAMCAM is the camera on the sample acquisition system. Other instruments include a laser altimeter, which is called OLA, to calculate the range from the spacecraft to the surface, and also provide a 3D map of the asteroid. There are 3 spectrometers, OTIS, Osiris, and Rexus, which provide composition information about Bennu in varying wavelengths. And finally, the TAGSCAM system for sample retrieval. It's the big arm shown on the image, which captured a sample from the surface and transferred it to the return capsule, which is the circular area you see just to the right of the arm on the image of the spacecraft. The spacecraft itself was launched 7 years ago on an Atlas V rocket and placed through a trajectory which brought it close to Earth for a gravity assist maneuver a year later, and then intercepted Bennu in November 2018. The gravity assist allows for the use of less fuel and a smaller launch vehicle, and is very common in deep space intercept scenarios. Well, the spacecraft then spent several years at Bennu, finally collecting a sample and returning it to Earth. While the sample canister parachute back to our planet, the spacecraft itself is now en route to another near-orbit asteroid called Apophis, which and has been renamed as the Osiris-APEX mission for short. It will intercept Apophis in 2029, even though it is a near-Earth asteroid, which, if nothing else, reminds us, in the words of Douglas Adams, the famous author, that space is really big. To close out our discussion on the spacecraft itself, I'd like to share a video of the actual sample capture using TAGSCAM. As you'll see in a moment, the sample arm descends to the surface and actually penetrates it, as the surface is just a rubble pile. The TAGSCAM system then blasts out some nitrogen gas, which forces regolith into the capture mechanism, and then the arm and the spacecraft back away from the asteroid. The video lasts a bit over 10 seconds, but the operation took hours, except for the sample capture at the very end, which was over quickly. So we're going to start the video. And waiting for it to start here. I think we've got a technical problem. If we can start the video. There it is. Okay. A second to catch up here. So here you'll see it moving in, it'll hit the surface in a moment, and then blast away. You can see it blast away the material, and it captured, the original intent was to capture about 20 grams of material, but it was believed that more than 10 times that was retrieved, so it was remarkably successful. So on that note, I'd like to thank you for your attention. I hope you found this of interest, and I'd like to turn the presentation over to my colleague, Zena.
Okay, my name is Zena, and today I have the privilege of taking you on a journey into the fascinating world of NASA's Osiris-REX mission, a mission that has just made history by successfully returning a sample from the asteroid Bennu. This remarkable achievement offers us a glimpse into the secrets of our solar system's past and holds the potential to reshape our understanding of the cosmos. As you can see in the left picture, in a momentous event, a capsule containing rocks and dust from Asteroid Bennu touched down on Earth at 10:52 a.m. Eastern Time on September 24th in a carefully targeted area of the Department of Defense's Utah Test and Training Range near Salt Lake City. This achievement reflects the combined efforts of countless individuals who remotely guided the spacecraft on its journey since its launch in September 2016. From its arrival at Bennu in 2018, it spent nearly 2 years orbiting and studying the asteroid's rugged terrain before carrying out its primary science objective, which was the sample collection, on October 20th, 2020, and it left Bennu in May 2021, while these steps were meticulously planned and executed. The significance of the sample return cannot be overstated. The capsule was securely stored in a temporary clean room, like in a continuous flow of nitrogen. This nitrogen purge ensures that the precious sample remains uncontaminated by earthly substances, of course, preserving its scientific value. The sample, weighing around 250 grams, is a treasure trove of information about our solar system's history. The journey does not end here, though. In fact, it's just the beginning. Here on the right, you can see Osiris-REX's asteroid sample canister with its outer lid lifted at a newly built curation facility at Johnson Space Center in Houston. And on the left, Osiris-REX asteroid sample canister cracked open for the first time in more than 7 years. The Bennu sample will soon find its way to the hands of dedicated curation scientists who are going to create a comprehensive inventory of the collected rocks and dust, and then distribute pieces of Bennu to scientists worldwide. This distribution marks the beginning of an extensive scientific analysis that promises to unlock the secrets held within these extraterrestrial materials. But why Bennu? What made this asteroid so special that it became the target of Osiris-REX's meticulous journey? Bennu is more than just an asteroid. It's a near-Earth object, or it's a near-Earth asteroid, making it relatively easy to reach in our quest for understanding the cosmos. Bennu's orbit around the Sun takes about 14 months, and it comes close to Earth every 6 years. This accessibility played a vital role in the mission's planning. Furthermore, Bennu's size and spin rate made it an ideal candidate, measuring half a kilometer in diameter and rotating slowly on its axis every 4.3 hours. Bennu's characteristics allowed Osiris-REX to approach, map, and collect a sample with relative ease. Lastly, and perhaps most intriguingly, Bennu's composition held the promise of uncovering ancient secrets. Primitive asteroids like Bennu serve as time capsules, preserving material from the dawn of the solar system. Spectrometers on Osiris-REX confirm that Bennu is rich in carbon-based molecules, including organics that are essential for life. This composition could provide vital insight into the formation of our solar system and the origins of life on Earth. In conclusion, the recent return of the Osiris-REX sample capsule from asteroid Bennu marks a historic achievement in space exploration. It not only demonstrates humanity's ability to reach out and touch the cosmos, but also holds the promise of unraveling profound mysteries about the universe and our place within it. As we move forward with the analysis of these precious samples, we stand on the threshold of new discoveries that will deepen our understanding of the cosmos and inspire future generations to continue exploring the wonders of space. Well, everyone, You've been listening to Alumni Carswell Observatory's monthly Teletube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Jatin, Paul, Zena, Maheen, and myself, Zena. Make sure to leave any comments or questions in the comment section of the video and talk to us in the chat right now. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to make a donation, see our website at yorku.ca/science/observatory. You can always connect with us on Twitter with the handle @YorkObservatory, and check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory. Thanks for tuning in. Clear sky and have a good night.